right, this is going to be the video for differential equations, section 8.3, the second day, where we're going to cover the variation of parameters method to handle non-homogeneous systems of differential equations. This method is a little bit more involved than the undetermined coefficients method, but this method works in pretty much every case. So this is the more generic method that you can always rely on to work. I will go ahead and try to kind of explain the derivation of it here. And then we'll go through one big example because it's so procedural that I really only need to show you one because they work exactly the same way every time. All right, in the previous section, we learned the method of undetermined coefficients, the table method, which is really nice if it works, but it's faster, only works in some cases. This method is called the variation of parameters. Here's the way it's set up. If we assume a homogeneous system, first of all, of the form x prime equals ax, and it has a solution of the form c1 times the first solution plus c2 times the second, and so on, then we know that the parts that make that homogeneous solution up those solutions form a fundamental solution set. And if that's true, we could write the general solution in this form, right? That's what we've been doing. We've been doing c1 times the first solution plus c2 times the second solution, and so on, for a new constant for each solution. Mostly we do systems of two, but we could have done a couple with three. This is extendable to any number. Okay, so what we're going to do is we're going to say, all right, well, this solution, whatever it is, like it's going to end up being some function of t for the x, for the y, for the z, and so on for each of these, right? Each of these is some function of t. Could be a constant, could be a function, right? Something like that. And there's one for each row in the matrix. Okay, so I'm going to call this x11, x21, all the way down to xn1. This second solution is x12, x22, all the way down here, and then all the way over here to x1n, all the way to xnn. And they're each multiplied by their own solution constants. All right, so then if you consider that we're multiplying these constants in, we're really getting c1 times all of these first constants, and this should be a c1 here, and then c2 times all these constants, and c3 times all these constants, right? So we could split this up a little bit differently. I could say, let's just take all these, vectors here and load them up into a matrix that then is multiplied by another matrix just with the solution constant. So we'll put the c1, c2 all the way up to however many we need in one matrix, n by one matrix, and then we'll take all the solution things, all of the forms of these terms with the e to the two t's in them and stuff like that, and we'll bundle all those together into a matrix. Okay. Well, okay. Realizing these plus signs should not be here. Okay, we're just having well, no, I guess we could do that. That's fine. Yeah. All right. And then if I wanted to express this as a matrix times a matrix, I can say, if you just build a matrix of all of these functions and multiply it by another matrix with all the coefficients for the multipliers for each of the solution terms, you could write the solution x as the product of two matrices. One of them is going to be a matrix of functions, and the other one's a matrix of just the c constants. Okay, this matrix of functions is called the fundamental matrix of the system. Okay, and usually we use a capital phi here. So it's the same as this phi, except it's the capital version, a capital phi, and it's a function of t in general, and it's a matrix. It's a matrix of functions. All right. So if we can find that function there, because of the way the fundamental matrix is defined, the determinant is the same as the Wronskian of the fundamental solution set, right? The determinant of that turns out to be, if you carefully look at when we define the Wronskian for a solution set, it matches the form of the Wronskian of those solutions. And therefore, because this is a linearly independent solution to the system, we know that Wronskian and therefore the determinant would be non-zero, which means that the inverse of this fundamental matrix must exist. In other words, if we are able to find this fundamental matrix phi, we will be able to find an inverse matrix phi inverse. Okay, and because every column of phi is a solution vector, it means that this matrix here represents a solution to the system. I should be able to plug it into the system and say phi prime equals that coefficient matrix times phi. So far, we're just talking about homogeneous systems. Okay? All right. So if we now have a non-homogeneous system, and the solution is this solution for the corresponding homogeneous solution is the complementary solution of the corresponding non-homogeneous system. To get the particular solution, we're going to do something like we did back in 4.1. If you recall, we had a function, right, which had a complementary solution that was like in some form, like let's say C1 e to the negative x plus C2 e to the 2x or something like that, right? And we're going to say that the other solutions, we're going to postulate a yp. Remember we said we're just going to replace this with a function times e to the negative x, some sort of a function u. If you recall, we did that. We postulated that there was some function of the variable times the complementary solution to get the particular solution. We're going to do something like that here. We're going to say that we're going to postulate that the particular solution is the fundamental matrix, which itself is a solution based on the corresponding homogeneous equation, times some other vector u. Okay? And because that could also be a function of t, we're going to take a derivative of that using the product rule. So x prime p, the particular value derivative, is going to be the first times the derivative of the second plus the second times the derivative of the first. And that means that we should be able to plug this in to x prime in the system. So if we have a system which is x prime equals a coefficient matrix times x plus an F matrix for the non-homogeneous part, if we plug this in for this x prime, we'll get this equals a times, and then for this we're going to plug in phi u plus the F. Okay, but we can actually replace this phi prime here, right here, with a phi prime because we know that the fundamental matrix is a solution of the homogeneous equation. So if you replace this with this, you get this. And then that means that you have an a phi u on both sides, so they can be subtracted off. And you'll end up with phi u prime equals F. Since we know that the inverse of phi exists, that means we can multiply on the left by the inverse of phi to get the identity matrix, and therefore u prime will be equal to the inverse of phi times F. That's kind of like when we said that u prime was equal to the modified Wronskian over the Wronskian, and then we ended up having to undo that by taking the antiderivative. We're doing kind of the same thing, except that this time it's a matrix with u prime is equal to an inverse phi times F, and then we're going to have to undo that by taking the integral of that to find what u is. And then that means that the particular solution will be the original fundamental matrix times this u, but that u is the integral of the inverse of phi times F. And then when you add that onto the complementary solution, it means that the general solution will be the complementary part, which is just the fundamental matrix times the vector c for the different C1, C2, and so on, plus this term to handle the non-homogeneous part, which is going to be the fundamental matrix, and then times the integral of the inverse of the fundamental matrix times the non-homogeneous part matrix, and then all of that integrated with respect to the independent variable t. So that's crazy looking, and we're going to have to go through carefully an example so you can see what it looks like. It's not as bad in practice as it looks, but it is kind of weird looking. All right. Now, for us to be able to do this, we're going to have to be able to take an inverse of a matrix, okay? So that's pretty straightforward to do with a calculator. If you have numbers, you just plug it in the calculator, but we're going to have to do it by hand because these matrices are going to have functions in them. So I'm going to show you a method right now to do this for 2 by 2, and then we'll look at a 3 by 3 example a little bit later, not in today's video, but in a later part of the course. But for now, I'm just going to show you how to do by hand a 2 by 2 matrix inverse. If you have a matrix, we're just going to use A here, which has got the elements A, B, C, D, whatever they are. They can be constants or functions. And the first thing you would do to finding the inverse is you're going to find the determinant of that matrix, which we know is this times this minus this times this. Okay, it then turns out that for a 2 by 2 matrix, the inverse of that matrix is 1 over the determinant times the original matrix but modified. What you're going to do is you're going to swap the two elements that are on the main diagonal, so D and A swap, and then for these other two elements, you make those negative. They stay in the same position. So it's a memorized procedure. That's how you find the inverse of a matrix if it's 2 by 2. There's a more complicated method when we have 3 by 3. We'll talk about that on another day. Okay, so let's do a two-dimensional system here, and we'll do it carefully, step by step. This is the last slide just to go through this example completely. All right, so we've got this system. The first thing we have to do is find the solution for the corresponding homogeneous system. So I've got, here's the whole matrix. It's x prime equals -3, 2, 1, -4, x, and then we've got this over here, which is 3t and e to the -t. So that's the non-homogeneous part. But first we're going to solve this. And so we'll solve that with the determinant to find the eigenvalues, 3 minus lambda, 1, 2, -4 minus lambda equals 0. So we'd have -3 minus lambda times -4 minus lambda minus 2 equals 0, which turns out to give the characteristic equation lambda squared plus 7 lambda plus 10 equals 0, which is factorable actually into lambda plus 2, lambda plus 5 equals 0. So we get two eigenvectors, -2 and -5. Okay, and then for each of those, we can go ahead and find the corresponding eigenvectors. So for the lambda is -2, 1, we would have -3 minus -2, which is plus 2 here, right? And we're going to end up with 1, and then 2, and then -4 minus -2, 0, 0. So we're going to end up plugging in -1, 1, 0, 2, -2, 0 into a matrix to get the equations to establish the k's. So that turns out to be 1, 0, -1, 0, 0, 0. So we end up getting that 1 times k1 minus k2 equals 0, or k1 equals k2. So the simplest vector we can use is 1, 1. Okay? And then for the second eigenvalue, -5, we'll have -3 minus -5, so plus 5, 1, 0, 2, -4 plus 5, 0, ends up giving me 2, 1, 0, 2, and then 1, 0. Right? So after RREF, we'll end up getting 1, 0, 1/2, 0, 0, 0. So we've got K1 plus 1/2 K2 equals 0. So we end up with K1 has to equal -1/2 K0, K2. And that gives us the eigenvector. Well, there's a number of them, but I'm going to go with 1, -2. So I'm going to plug in 2 here. -2 to make the negative go away, so that's 1. Okay, and in the end, then we get this complementary solution here, which is C1 times 1, 1 e to the -2t plus C2 times 1, -2 times e to the -5t. All right, so there's the solution, general solution for the complementary system. Complementary solution for the corresponding homogeneous system. All right, the next thing we're going to do then is we're going to do this new method. And what we're going to postulate is, so I'll use a different color, we're going to postulate that we're just going to use the new equation. So this will be on a formula sheet that for xp, we're going to use phi, integral of inverse phi times f. These are really matrices, dt. Okay, so first we need what is phi. Okay, so phi is the fundamental matrix, and it means we're going to ignore the C1 and the C2, but we're going to take the corresponding part here. So this is 1 e to the -2t, and then the y is e to the -2t also. And then over here it's 1 times e to the negative 5t, so e to the negative 5t, and then this was negative 2 e to the negative 5t. So this is how you form the this fundamental matrix for the system. You just ignore the c, and you just take 1 times this, 1 times this, 1 times this, negative 2 times this, and form that into a matrix. Okay? So because of the way the structure is defined here, this will have an inverse. And the next thing we're going to do is find the inverse. So the inverse, first to do that, we're going to have to compute the determinant. So the determinant of this computed by hand is going to be e to the negative, let me just write it this way. The determinant of phi is going to be e to the negative 2 times negative 2 e to the negative 5t minus e to the negative 5t times e to the negative 2t. Okay, so that's going to be negative 2, and then e, and when I add negative 2 and negative 5, I'm going to get negative 7t, and then minus on e to the negative 7t. So if I have 2 minus 1, negative 2 minus 1 is going to give me a negative 3 e to the negative 7t. So this is the determinant. And then that means that the inverse matrix is 1 over that determinant, which is negative 3 e to the negative 7t, times a matrix which is the original phi matrix but manipulated. What we have to do first is reverse the things that are on the main diagonal. So the negative 2t, negative 2 e to the negative 5t goes here, and the e to the negative 2t goes here. And then for the other things that are not on the diagonal, we negate them. So e to the negative 5t negative, and negative e to the negative 2t. Okay, so the next thing we're going to do is we're going to basically multiply in this 1 over determinant part. So this is going to end up being, let's see, we have a negative divided by a negative, so that's going to just be positive 2/3. E to the negative 5t divided by negative 7t is the same as, is going to be like, see, negative 5 minus negative 7 is negative 5 plus 7, which is e to the positive 2. So this will be e to the 2t. This one over here is going to be a negative 1 over a negative 3, so it's negative 1/3, or sorry, it's positive 1/3, and then also e to the 2t. Okay, this one down here will be negative 1 divided by negative 3, so that's positive 1/3 e to the negative 2t minus 7, so 2 minus negative 7 is 2 plus 7 is 5t, right? And then we'll have a positive divided by a negative, so that's negative 1/3 e to the 5t. So this matrix here is the inverse matrix of the fundamental. Okay. Now we're ready to plug all that stuff into what we had. So here's the form again. Let me change colors. We know that the solution for the particular one is phi times the integral of inverse of phi times f dt. Okay, so now let's plug these in. The phi matrix is it's going to be e to the negative 2t, e to the negative 2t, and the second row or second column is e to the negative 5t, negative 2 e to the negative 5t. Okay, and then we have to take the integral of the inverse phi matrix, which is 2/3 e to the 2t, 1/3 e to the 5t, 1/3 e to the 2t, negative 1/3 e to the 5t, times the F matrix. Now this is the part that's the non-homogeneous part up here. And so if we go all the way back to the original problem, that's 3t e to the negative 2t. So I have to put that in here now. We have 3t e to the negative t. And we're going to first multiply these matrices together and then do an antiderivative. Okay, so I'm going to just keep copying this down. I'll just put a dot here because we just let that copy down. But let's go ahead and multiply these two things together. We have a 2 by 2 matrix multiplied by a 2 by 1 matrix, which means we're going to get a 2 by 1 matrix, right? It's got 2 rows and 1 column in T. Okay, and so when we do that, we're going to have to multiply this. Let's see, it's going to be this times this. So that's going to be 2/3 times 3 is 2, right? And then we're going to have a t times an e to the 2t plus this times this. So that's going to end up being 1/3. E to the 2t times e to the negative t is going to be the same as e to the 2 minus 1 or e to the just 1t. Okay? And then on now over here, we're going to take this times this. So it's going to be 1/3 times 3, which is 1, and then it's going to be t e to the 5t. And then it's going to be this times this, so minus 1/3. E to the 5t minus a t is 4t. Okay, so we've got an integral of a matrix, which really means that we're going to have a matrix that has separate integrals. So what I'm going to do is say I've got a matrix here, and it's going to have these separate integrals. I'm going to have 2 integral t e to the 2t, or actually I'll just leave that as an integral inside there. So I'm going to have integral of 2t e to the t dt plus integral of 1/3 e to the t dt. And then this second row is going to be integral of t e to the 5t dt minus integral of 1/3 e to the 4t dt. Okay, we still have all this on the outside. We still have to do the integral, or we're doing the integral now. Sorry, I erased it. 2 integral, and this is integral. Okay, good. There we go. All right, this first one here is going to require integration by parts. So let me do that over here on the side. And this is going to be integration of 2t e to the t dt. So maybe I could say u is the 2t and the dv is the e to the t dt, so that du is 2 dt and v is e to the t, so that we have uv minus integral of v du. So it's going to be 2t e to the t minus 2 e to the t, right? 2t, is that right? It's 1/2, I think. Yeah, okay. Just making sure I'm checking against my key here, and I'm seeing that there's a slight discrepancy. I don't want to introduce a mistake here. So yeah, I think I might have dropped a constant in here. Okay, let me continue here. I'm going to continue this, and then there's a posted solution here. If I make a mistake here, look online for the posted solution, because yeah, if I made this 2t, then dv would be e to the t dt, so then this would be 2 dt, and that would mean uv, right? So 2t e to the t. Yeah, I think what I have here is it's slightly wrong, right? Because, or what I have posted. So if I bring the 2 out here, the antiderivative of that is e to the t. So this is going to be what we get when we replace that. In fact, let me do that in the next step. We're going to replace that with 2t e to the t minus 2 e to the t. And then I have to do this integral, which I can just directly do. That's 1/3, and then the antiderivative of e to the t is e to the t. This one here is also going to require integration by parts. So let me do that off on the side. T e to the 5t dt. We would set u equal to t, dv equal to the e to the 5t dt. So du would be equal to dt, and v would be the copy, but divided by 5. So we're going to have uv. So that's 1/5 t, 1/5 t e to the 5t. 1/5 t e to the 5t minus integral of v du. So that's going to be a 1/5 e to the 5t dt. So that's going to be, is that right? Oh, I think I see what happened here. I made a mistake in this version. So I should have copied a 2 here. That was the problem. There's a 2. Let me go back and fix this. I want to make this right. Sorry about that. So yeah, so I forgot to copy this 2 right here. But there is a 2 there. And that means that integration by parts is, let me do that again, to e to the 2t. So where's that 2 going? All right, so now let's do this. 2t dv equals e to the 2t dt. du equals 2 dt. V is e to the 2t, but divided by 2. Right? Okay, so then uv, the 2's cancel, and we just get t e to the 2t minus integral of v dt, which means the 2 comes out here. So that's going to cancel v du. And so this will just be t e to the 2t minus the integral of e to the, or minus the integral of that, which is e to the 2t divided by the constant. So yeah, so that, let me fix that. And that matches what I have in my posted key, which is correct. Okay, so this is t, yeah, t e to the 2t minus a half e to the 2t, and then the antiderivative here, which is 1/3 e to the t. There we go. Okay. Now the second row, which is integration by parts, is where we're getting ready to do. We're going to do integration by parts for this, t e to the 5t. So we'll make u equal to t, dv is e to the 5t dt. So du is equal to dt, v is equal to 1/5 e to the 5t, uv would be 1/5 t e to the 5t minus integral of v du, which would give me 1/5 t e to the 5t. When we do this integral, we'll divide by 5 again, so we'll get 1/25 e to the 5t. So that's what we're going to get when we do the integral of this right here. Then we get 1/5 t e to the 5t minus 1/25 e to the 5t. And then the antiderivative finally of this is minus, let's see, when we're divided by that 4, it's going to be minus 1/12 e to the 4t. All right. So, and we're still not done, right? That's just taking the integral. Now, what we have to do is that integral, which produced a matrix of 2 rows, we still have to multiply it by 5 by the fundamental matrix. So I'm going to copy it again down here. I'll erase this now. And let me copy it again. 5 is e to the negative 2t, e to the negative 2t, e to the negative 5t, negative 2 e to the negative 5t. Now we have to do matrix multiplication. Okay, so let me change colors here so we can kind of see. It's going to be this times this first. Well, first of all, we have a 2 by 2 matrix times a 2 by 1 matrix, which means we're going to get a 2 by 1 matrix. So it's going to have just 2 rows in it, right? And the first one's going to be this times this, which is t e to the, well, when we take e to the negative 2t and e to the positive 2t, that's going to be e to the 0, which is 1. So that's just going to be t, the one of the negative side here, t. And then this times this term, which is negative 1/2. Okay. And then we've got this plus 1/3, but this time it's e to the negative 2t times e to the t, which is e to the negative t. Make sure I'm not introducing some problems here. T minus a half plus 1/3, yep, okay. And then I have to take plus this times this, right? So that's going to be 1/5 t, e to the negative 5t and 5t cancel. And then I've got minus 1/25, just the 1/25, and then I've got minus 1/12 e to the negative 5t times e to the 4t, which is going to be e to the negative t. Okay, so that's the first multiplication. And then we're going to do the same pattern except down here. So I'm going to take this times this, which is t e to the negative 2t times e to the positive 2t cancels to e to the 0. And then I've got times this negative 1/2, and then they cancel. And then I've got the 1/3 e to the negative 2t times e to the positive 1t is e to the negative t. And then finally, let me use a slightly different color here, like orange. we're going to take this times this. So that's going to be negative 2/5 t e to those cancel. And then I'm going to have negative negative, so positive 2/25. Okay, positive 2/25, and the e's cancel. And then I'll have positive 2/12, which is the same as 1/6, and it's going to be e to the negative t. All right. So after all of that, we've got that. Now we can combine some like terms if we have them, which we do here. Let me go back to blue, and we'll combine like terms here. So what we've got is, we've got some terms that have a t in it. We have a t and a 1/5 t, so that turns out to be 6/5 t. We have a constant term, negative 1/2 and negative 1/25, which turns out to be negative 27/50. And then we've got these e to the negative t terms. 1/3 minus a 12th turns out to be plus 1/4 e to the negative t. We combine terms in the second row. The 1t and the negative 2/5 t combine to give me 3/5 t. And then I've got this constant term, negative 1/2 and positive 2/25, which is negative 20/50. Then I've got the 1/3 and the positive 1/6, which turns out to be 1/2 e to the negative t's. And that is what xp is. Okay, so after all of that, we get xp. Much, much more time consuming than the table method, but this method will work all the time. And there's no danger of absorption or any other weirdness happening. Okay, then finally the general solution would be the complementary solution plus that. So let me put them all together at the end. Okay, now that we have our xc and we have our xp, we can just finally just state that the general solution is equal to xc plus xp. And that's it. So these together form the entire solution. All right. Now that's pretty dang intense, I would say. In fact, let me just write it one more time to show you the way it probably will show up if you see it in the textbook. It'll say x, it'll say x is equal to c1, 1 e to the negative 2t. So there's some stuff in the solutions related to e to the negative 2t. And then there's going to be c2 and a vector for e to the negative 5t. Then you'll have 6/5 and 3/5 for the t component. You'll have a constant matrix, which will be negative 27/50 and negative 21/50. And then you'll have 1/4 and a 1/2 times e to the negative t. That's probably the way the answer will be written. All right. So one really intense example, and I think from that, if you follow that procedure every time, you're going to get that right. It's tricky, but it's doable. All right, so that'll be it for that. There's a couple of other things we're going to talk about to finish up the chapter. Those will be covered in further examples. And I do believe at some point in these videos, I am going to talk about how to do an inverse for a three-dimensional system. I believe that comes up in one of the other examples.